Well, this is John Black, Super Chemist. We're on port, I think, 3. What was I trying to get to? What was my point in the last video? At the end of the last video, okay? The electron's moving, right? It's vibrating as it moves, so it goes on this path, right? You want to take a picture of it. It's too small to see, so you throw some photons. Right here, the photon hits the electron, and they collide. The photon comes back to your camera or your computer, and it makes a picture for you to see. Okay. Now, when you see that picture, it doesn't show you a picture of the sine wave. Okay. It doesn't show you a picture of the path. All right. All right. All you can know is that at this point, a photon hit the electron and bounced back. You know the electron was right here. Why can't you know the momentum? You know what I mean? If you have a baseball going this direction, just like the electron is going in this direction, and you hit something at it, you know where the baseball is going to go, right? You know the momentum. See, an electron doesn't move like a baseball. It doesn't move in a straight path like that. It moves in an up and down, oscillating, up and down, jiggity jaggedy type of thing, right? So when we hit it with the photon, we don't know if the momentum of the electron is going down like with this x, or up like this x, or horizontal like this x. We don't know the momentum because we can't see that sine wave. We can't see that whole path, right? All we can see is that position, okay? So this is why we can never know the momentum and the position perfectly well, because we can never see this path, this sine wave path, this oscillation, right? So we'll never know. We can't add up this electron is going like this, and then we hit it with a photon, and then we know where the momentum would go. We know where the electron would go, because the electron isn't doing that. It's going up and down, unless we know if it was going in an up, direction, or a down direction, or a horizontal direction. You know what I mean? Unless we know that, we can never know what the momentum is exactly, where that electron went after we hit it with the photon, right? As long as he's going, somewhat horizontal, like on these troughs and these crest, then we can kind of know where the momentum will be, because he's kind of going the way baseball would be, horizontally, right? But what about these ones going up and down? You got half of the sine wave is going in a direction that is perpendicular to the overall direction of the electron. So the overall direction is going like this, left to right. But you can see when you vibrate, you got half of the time, and at least half of the time, where the momentum doesn't correlate to the path of the electron. It correlates to up or down. You know what I mean? So there's where your uncertainty comes from. That's like, how can you know the real momentum of a electron if you can never see this up and down oscillation? All you see is a straight path like this, right? You can never see, because your momentum is changing as he vibrates. The electron, the momentum is going down here on the first x and going up here on the second x. It's going horizontal on the last x. You can never know that position of the electron in its oscillation. You can never know it. It's too tiny for you to see it. Okay? And if you take a picture and sure, the electron was right there, right, where that dot is. That's where the electron was. But where was the sine wave? Was the electron going up or down in its oscillation? Because that will tell you about the momentum after you hit it, right? If the electron was going down when you hit it, the momentum is going to be different than if the electron was going up when you hit it with the photon, right? The physicist can't know where on this sine wave, the photon that we threw at it, where on the sine wave did the photon hit it, right? And if you don't know that, right, if you don't know whether it's this x, this dot, if you don't know where they collided, right, then you don't know the momentum, or you don't know where the electron went after that, right? Because if you hit it here, right, you can plainly see the momentum is pointing this way, right? But what about that second x? What if you hit it at that x? Oh, well, now the momentum is this way. Okay, so it all depends on where on that wave path of the particle electron is at. I need to know that to know this. That's why you get uncertainty. Because you can't tell. You can never tell. You will never know. That's why they relate it to this 2 pi crap and this, because they're talking about this cycle. This cycle, you don't know. You don't. And if you know the momentum, right, you don't know. Because what if you check the momentum when it was there? Right? and like I said, the momentum is down. What about the second X? What if you checked it there? Now you'll never know the both position and momentum because of this sine wave, and you'll never be able to take a picture and know where did that photon that you threw to take your picture. Did it land here, 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 here? I mean, what direction was the electron moving or vibrating, right, when I hit it with that photon? All right. Now, why can you never know the position? If you know, let's say you know the momentum, it's going this way, it's going from left to right, right? Why can you not know the exact position? Because it oscillates. The path going left to right is oscillating up and down. Therefore, you can't know if it's oscillating down to a trough or to the crest in between. So the position is never known, right? Even if you know the exact momentum, it's going this way, the electron, right? Left to right. You still don't know the position because as it's moving over, it's going like this. This is what it's doing. You know what I mean? So it's hard to get its position, right? It's hard to get its momentum when he changes its momentum, a whole bunch of millions of times every second because it's vibrating up and down. Well, let's go over some dry facts about the double slit experiment. So I'm going to actually start doing this experiment. But you got 2 slits, right? What is the width of these slits? Well, basically, they want you to have it be if you're working with 400 nanometer light, they want it to be 400 nanometers or smaller. If you're working with 700 nanometer light, then they want the slit to be 700 nanometers or smaller. So whatever the wavelength is, it wants to be comparable to this, or this slit needs to be smaller or comparable. So you can see, UV light starts at 400, red light starts at 700 nanometers. And remember, nanometers just means 10 to the minus 9th meters. So 550 nanometers, I took green in between. I would just take that nanometer off, put 10 to the minus 9 meters, right? And then I move my decimal so I can get this. This is the same meters. These are all the same, right? That's if you're working with, visible light. A common setup. Here's a common setup. Here's the millimeters, micrometers, but I like this. 2 times 10 to the negative 5th meters. And this was 10 to the 7th, not minus 7th meters, right? This is a common setup. This is for visible light. So what about the distance in between the slits, right? And it says about 0.1 to 0.5 millimeters apart, which is 10 to the negative 4 meters apart, okay? Now, just so that you can see the difference, you know what I mean? So, because it's just going to be 2 little slits like that, you know what I mean? You ain't even going to barely see them, all right? Let's make them larger, though, so that these are our slits, right? Now, I put a thickness of this as 10 to the minus 6, right? Because that's in between 10 to the minus 7 and 10 to the minus 5. It's just an arbitrary whatever, right? The separation, right, I put as 10 to the minus 4, right? So that's what you're supposed to have about that, right? So that's about 25, because I changed it so that they both have 10 to the minus 4. And then I just seen what was the difference between 0.04 and 1. It's 25, right? This one is 25 times bigger than this, right? The thickness. So I drew this. It's kind of to scale. It's not perfect. I didn't get my roller out or anything like that. But if this slit right here, these 2 slits, if they were 10.-4, right, meters, you get 25 times. I basically put 25 of these slits in between here that you can't see because I didn't put slits, I just put the length. But you can see there's a large distance between there when you put it up to, make it bigger, you know what I mean? But when you scale it down, right, it's going to just be like that, right? And the reason I wanted to do this, right, is because I want you to understand, when you do this experiment and you have, say, a laser on this, right, the laser is going to cover both slits, you know what I mean? You're either going to edge them on both slits, or, you know what I mean? You can see how I put a circle here. That would be the laser, right? It encompasses both, or at least part of both slits, right? So, and to make it a scale, you can see right here, look. You see this blue line, right? This is the circle. This is the laser. Everything inside here, if this was a double slit experiment, this laser would be like, here. It would be, it would encompass this whole thing area here. You know what I mean? Okay, so for a laser, right, the slit width is very narrow, right? 10 to the 20 micrometers. That's 10 to the negative 5 meters. And look up here, 10 to the negative 5 meters. That's common setup. It's not really whatever, you know what I mean? It's smaller than 2 times that or 4 times that. But, for an electron, right, instead of a laser, instead of using light, you're using an electron. The slits are even smaller, at nanometers instead of micrometer scale, right? So, example given, 100 nanometers, that's 1 or times 10 to the negative 7th meters, or just 10 to the negative 7th meters, okay? And that's smaller than this, right? And it's smaller than this. The main thing is the requirement, the slit width must be comparable or smaller than the wavelength of the light being used, okay? If you want a clear, wide diffraction pattern, you know what I mean? If you want it to look good, you can see stuff from it instead of just some blur, you know what I mean? So if you have a slit this wide, you need the wavelength to be either that wide or bigger. You want your slit to be smaller or equal to the wavelength, length of the wave. Now, first thing I want to dispel is this idiotic thing where they always compare this stuff to baseballs and bullets and stuff like that, right? And they'll say, oh, well, if you have a baseball and you throw it through 2 slits, it'll form two pals, and you'll just have a whole bunch here and a whole bunch here. There'll be no diffraction. None of this stuff is going on. This is what they're saying, right? And they're right, you know what I mean? But it's misleading. It's misleading, just like this flashlight, right? They'll say, oh, well, you can't have it being these particles coming out, and it's not this wave. It's something in between. Yeah, it's particles. Now, I drew the paths of the sine wave, the path that it cuts out, the light photons, right? You wouldn't see that, though, right? If you take a picture, it'd just look like particles. You wouldn't see the movement. This would be like stink lines, you know what I mean? You don't see stink lines when you're running. You don't see lines like that when balls are moving fast, okay? And you don't, but the photon is vibrating as it moves, so it does cut out a path that looks like a sine wave, okay? The photon, see, this is wrong because the photon is not a wave, right? This is somewhat wrong, but really right, because it's not showing that the particle is vibrating. See, this is the way it should be, okay? And for them to say, well, look, when bullets come out, they don't act like waves and blah, blah. Yeah, that's because bullets are giant. Baseballs are giant, okay? That means the de Broglie wavelength is very tiny, like it's a Planck length, okay? Which means, your de Broglie wavelength, that's telling you the distance you're vibrating. If you're only vibrating a Planck distance, or Planck, 10 to the minus 35 or 6, or 34, meters, that's nothing. No one's going to see that. It's not going to affect anything. It's not going to do